Everyone. Welcome to this last session of today's SIGCOMM conference. So now what we are going to do is we're going to have a session on programmable data planes. There are 5 amazing talks in this session. So I think without any further ado, I'll start with the first talk. So the first talk is about programmable packet scheduling with a single queue. The speaker is Zulong Yu. He's a fourth year PhD student at Johns Hopkins University. He's working on programmable networking and network systems. And he's actively looking for internship, job, and collaboration opportunities. Please contact him after the talk if you see a good fit with his research skills. So with that, we'll turn the video on.
Hello everyone, this is Zhuolong Yu from Johns Hopkins University. Today I'm glad to share our work, Programmable Packet Scheduling with a Single Queue. There is a long history of designing packet scheduling algorithms. A lot of packet scheduling algorithms have been proposed for different objectives, but most of them are not deployed in practice yet for real network traffic. The main reason is that there is very limited hardware support for these algorithms due to the high cost to design and deploy switch ASICs. To address this problem, programmable packet scheduling emerged in recent years. The key idea is to decouple the packet scheduling algorithm from the switch ASICs. It enables the algorithms to be programmed into the switch without changing the hardware design. And it brings 3 advantages: easy to develop, easy to customize, and easy to test. Typho is a popular approach proposed in recent years to realize programmable packet scheduling. The basic idea of Typho is to associate a rank with each packet and maintain a sorted queue based on the rank to buffer packets. The newly arrived packets are inserted based on their ranks, and the packets are dequeued from the head. With that, different packet scheduling algorithms can be implemented on top of Typho. However, despite its coolness, it's still challenging to implement Typho in practice, especially for switch ASICs. Because Typho requires a new ASIC design and its design is not scalable enough. SP Typho is a very interesting work which approximates Typho and can run on existing hardwares. The basic idea is to map the ranks into a set of priorities, and then schedule the packets with a set of strict priority queues. Their result shows they can approximate Typho pretty well. However, the implementation of SP Typho requires multiple strict priority queues, while in some cases, these hardware queues are precious and should be used for other applications, like performance isolation between tenancies, for example. So we ask a question: what's the minimal number of queues to achieve programmable packet scheduling on existing hardware? To answer this question, let's first think about what does packet scheduling do. In some sense, we can consider that it's doing 2 jobs: maintaining an order for packets in the buffer, and dropping the right set of packets when the buffer is full. We observe that there are 2 trends in data center networks: shallow buffer in the switch and faster convergent congestion control algorithms. Both of them are critical to the performance of data center networks. With these trends, we argue that dropping the right set of packets is more important for packet scheduling. For example, when there are some elephant flows competing with mice flows on one link, dropping the packets or elephant flow is more important than the dequeue order of these packets. Based on this intuition, we propose our approach called IFO, admission in first out solution. So what's the right set of packets to drop? Typho is a very optimized approach, always putting the high priority packets to the front. So ideally, we want to drop the same set of packets as Typho. In this example, we have 6 packets coming. With FIFO, the first 4 packets get into the queue, and the last 2 packets get dropped when the queue is full. With Typho, the low priority packets get dropped when the queue is full. For IFO, if there is an oracle telling you to drop the right packets, for example here, if someone tells you to drop the packets with rank smaller than 3, then the admitted packet set is same as Typho. So our idea is to use automation control to approximate Typho. In such a way, we only need one queue. Our automation control will drop packets based on their ranks and drop packets even when the queue has room. Now we show how we do automation control. Our automation control has 2 components, the temporal component and the spatial component respectively. The temporal component means that the packets with the same rank are treated differently at a different time. For example, when a packet with rank 3 comes, if the queue is almost empty, then the packet is admitted. If the queue is almost full, then the packet is rejected. The spatial component means that at the same time, different packets are treated differently. The queue is same full here. The packet with rank 3 still cannot get in, but a packet with rank 1 will be admitted. At a high level, the temporal component is to handle the discrepancy between the arrival rate and the departure rate, and the spatial component tries to capture the relative rank of the arriving packets. Our automation control uses the queue length as an indicator. When the queue length grows, it means the arrival rate is larger. When it decreases, it means the departure rate is larger. For the spatial component, we use a sliding window to track the ranks, and we use quantile to express the relative rank. The quantile here means for a given rank, how many values inside the window is smaller than this given rank. We will show how to compute the quantile in the data plan later. For the temporal component, we use the queue length and the queue size to capture the discrepancy. For the spatial component, we compute the quantile of the packet rank in this sliding window. We combine the 2 components into one condition, and we use this condition to decide whether to admit a packet or drop a packet. Without getting into much detail, we give an example here to show how FO works. Here we have a packet coming. Assume the quantile of its rank is 50%. When the queue length is 2, we can compute the threshold is 80%, which is larger than the quantile. So the packet is admitted. However, in the right figure, if the queue length is 5, then the threshold is smaller than the quantile. As a result, the packet shall be dropped. Now we show how we compute the quantile. We use a sliding window to record a set of packets and compute the quantile with this window. However, it's very difficult to maintain a plain sliding window on switch ASICs. In practice, we use registers in the switches to store the ranks, and each register corresponds to one cell in the sliding window. Each stage in the switch pipeline can have multiple cells to store the ranks. In front of the registers, we have an index tagger to maintain the index for the packets and decide which index is the current head of the sliding window. Here we have a packet with rank 5, and the index tagger gives the packet index 4, which means the head is at cell 4. We also have a sampler module which feeds one packet into the window for every n packets, so that we can approximate a larger window with given resources. We compare the rank of the packet with the ranks in the sliding window and compute the quantile for the packet. At the same time, we also update the cell at the head of the sliding window. In this way, we can maintain the sliding window in the data plane and get the quantile for each packet. We implemented Typho on a barefoot final switch, and we have performed both testbed experiments and large-scale simulations. We evaluate a wide range of aspects of Typho. In this talk, I will only show some of these results. Please refer to our paper for more detailed results. First, we show how Typho works in a data center setup. We compare Typho with several state-of-the-art solutions. We change the traffic load and check the FCT for both small flows and large flows. According to these figures, Typho has similar end-to-end performance compared with other state-of-the-art solutions. Then we show how Typho performs on a hardware testbed. We have 4 senders and 1 receiver running DPTK to send and receive packets. The 4 senders start one by one every 5 seconds and send UDP traffic to the receiver. And we give different priorities to these flows, and the later flow has higher priority than the earlier flows. When we use FIFO, the bandwidth is evenly allocated to the 4 flows because it cannot distinguish these flows based on the priorities. While SP Typho and IFO can allocate the bandwidth for high priority flows, IFO achieves this with only 1 queue. Here shows the TCP scenario. The setting is similar. We also give higher priorities for later flows, and we can see a similar result that high priority flow dominates the bandwidth for SP Typho and IFO. So in conclusion, we show that we can use 1 single queue to build a programmable packet scheduling approach with existing hardware. Thank you. I'm happy to take any questions.
Yeah, so first of all, can somebody turn my video on? It seems like the host has turned it off, so I cannot turn it on. Awesome. So yeah, so great talk. So I think this is sort of like a work that is actually extending like a long series of work that have been happening in the last couple of years. So again, a great talk. So I will start with sort of like a question that I had when sort of reading through this paper. My question is, again, you may not have the answer to the second part, but the question is like, why do you think you came up with this idea and not the actual Typho developers? Like, what insight or what aha thing happened with you that, oh, this is something that we can do with Typho? Because it seems like it's something that is independent of Typho. So can you tell us a little bit about the background as to how you ended up with this sort of insight?
Yeah, the insight actually mainly comes from our observation of the 2 aspects, like the shallow buffer and the fast conversion congestion control. Yes, so in this way, we were thinking that now everyone in the network community, they are wanting the lossless network in such a way. If there is no packet loss, and also the buffer is shallow, we are wondering maybe the strict ordering of this packet inside the buffer is not that important. And if and if there is a slight packet dropping, we think if we are dropping the same set of Typho, but we are not maintaining the order, it should be fine. Yes, so we started doing this. Yeah.
Okay, cool. So so moving on with that sort of thing, there's a question like, okay, so is IFO sort of like equivalent to Typho in strength, or are there certain policies and scheduling policies you cannot implement with IFO?
I think any policies can be implemented by Typho should should also can be implemented by IFO, because we are just maintaining one rank before the traffic manager, and we do the automation control. Also, I also want to note that Typho actually cannot support pfabric because it will lead to auto order packet when the end host is running SRPT. But IFO does not have this problem because we are using one FIFO queue. After doing the admission control, we will not reorder this packet.
Okay, cool. Okay, so another question on that point is, so you are using, so is it like focused on programmable data plane? So again, I'm actually just summarizing the questions that are there on Slack. So like two folks have already asked this question. So this question is from Maria, asking about like, where do you run this thing in this switch? And I'm just adding to that question, like, do you need a programmable switch for IFO, or any legacy switch can work with this as well?
Yeah. Now we actually need a programmable switch. We need a stateful memory to maintain the states for the packet rank, and and we are implementing the logic on the ingress pipe. So in the ingress pipe, we decide whether to drop the packet. If we want to drop it, we want to drop the packet won't go into the traffic manager.
Okay, so I think we have two more questions here. So from Robert, we have, how would the behavior degrade if you are using EWMA, like weighted, like sort of moving average, instead of in place of a sliding window?
Yeah, for the moving average, we actually haven't tried that one, but it's quite interesting to try because if we are using moving average, we can save quite some stages in the program in the switch.
Okay.
Yeah. Maybe we can try it like later.
Okay, and then let me quickly go over this. Okay, so the other question is like, what are the resource constraints that you see when using this sort of building this sliding window on these switches?
Yeah, great question. So in our hardware prototype, we are using 4 stages for storing the sliding window. And each stage on Tofino, it can support like 4 cells. So basically, we are using 4 stages to store 16 cells, and we have a sample module. If like we are sampling every 1 packet for every 5 packets, then we can approximate like 80 slots.
Okay. So and I think I'll just take this as a last question. Like Jonathan has a question, which is sort of like I was like thinking of as well. Is like, first of all, do you think any improvements in P4 to make your logic simpler? Because again, P4 is a certain abstraction defined for routing and switching. Do you think like there might be a better logic or a programmable block that you can add in the P4 like language that is much more efficient in terms of resource usage and maybe allow you to do like bigger, higher sampling for your design?
Yeah, I think first of all, if we have more stages, it will definitely be better for our like IFO prototype. Yeah, because we can store more states here, and the estimation will be more accurate. And one strict effect is that the current Tofino implementation that with the current Tofino, we cannot get the queue length directly from the ingress pipe. So we need some extra effort or tricks to move this knowledge from the traffic manager to the egress, then to the ingress pipe, then read from the ingress pipe, which is kind of tricky. Yeah, so if we can read the accurate queue length info from the ingress pipe, it will also be great.
Okay, awesome. So again, great talk. So I think we'll move on with the next one. So the next talk is on Sailfish. Our speaker is Tian Pan. He's a visiting scholar of Alibaba Cloud, and his research interests include programmable data planes, data center networks, and also satellite networks. So I'll let the video turn on now.
Hello everyone, this is Tianpan from Alibaba Cloud. It is my honor to present our work, Selfish, Accelerating Cloud-Scale Multi-Tenant, Multi-Service Gateways with Programmable Switches. Selfish is gateway for the public cloud, which contains virtual private clouds, VPCs. First, we show where is the cloud gateway. From the figure on the left, we can see that the cloud gateway is at the central hub of the entire cloud to handle the east-west traffic from VM to VM, the south-north traffic from VM to the internet, and the IDC cross-region traffic from VM to the IDC or cross-region network. Typical cloud service examples are listed in the right table. There are two basic forwarding steps at the cloud gateway. The first is to find the right VPC scope containing the destination VM according to the inner DIP of the VXLAN encapsulated packet via the VXLAN routing table. The second is to find the exact physical server address where the destination VM is hosted according to the inner DIP of the VXLAN encapsulated packet, as well as the VPC scope obtained from the first step via the VM-NC mapping table. In Alibaba Cloud, the cloud gateway was originally built by software. However, with rapid growth of traffic, the software gateways encounter many problems. The first problem is high kpacks and opacks. Processing tens of Tbps traffic needs hundreds of software gateways. If safety margin is considered, the gateway number will be doubled. If disaster tolerance is also considered, the gateway number will be further doubled for one-to-one backup. Finally, the kpacks will reach tens of millions of dollars for a typical cloud region. The second problem is the huge gateway number will exceed load balancer's next hop count limit. We have to split one large gateway cluster into multiple smaller gateway clusters behind multiple load balancers with additional maintenance overhead. Last but not least is the CPU overload problem, which is observed from time to time in Alibaba Cloud. Traffic bursts will overload the CPU, which will further cause packet loss and affect user satisfaction. To handle the growing workloads, horizontal scaling is common wisdom in the cloud. But why horizontal scaling does not work this time? After analyzing the traffic captured during CPU overload scenes, we find that the top 1 and the top 2 flows dominate this traffic. That is to say, a small number of heavy hitters contribute to the load imbalance among CPU cores. On conducting flow-based hashing over the run-to-completion forwarding model, heavy hitter flows will possibly be hashed into the same CPU core, even though the hashing algorithm itself is perfectly random. Although packet-based hashing can achieve perfect load balancing, it will cause packet out of order, and it needs dedicated hardware for fast packet reordering. In history, the internet traffic growth is far beyond Moore's law, while Moore's law also goes beyond the performance improvement of CPU core. Based on these observations, software gateways will persistently be challenged by more and more heavy hitters in the future. To protect the cloud gateway from traffic floods, we naturally turned to hardware. There are 3 options at hand. The fixed-function ASICs are performant, affordable, and energy efficient. However, they are not the best fit for our cloud gateways, since fixed-function ASICs cannot well adapt to the rapid changes of cloud services. The FPGAs are programmable, but with limited performance. It is more suitable for building SmartNICs at end hosts rather than cloud gateways at central hub. Programmable switching ASICs, such as Typho, have both advantages of fixed-function ASICs and FPGAs. Besides, they have a similar unit price as software gateways. Applying programmable ASICs to cloud gateways also has many challenges. A large cloud region in Alibaba Cloud can have millions of VPCs and millions of VMs, leading to a very large VXLAN routing table and VM-NC mapping table. Besides, both tables have longer table entries compared with that of traditional devices. Storing these tables is easy for a software gateway, but difficult for programmable ASICs, because there is very limited on-chip SRAM and TCAM. Besides 2 major tables, the cloud gateways also need to store other tables such as ACL rules, meters, SNAT, and DNAT tables. Some tables are stateful and very huge. The cloud gateway also faces challenges to process more IPv6 traffic. First, IPv6 entries are much longer. Second, dynamic memory allocation for both IPv4 and IPv6 entries is needed. The last challenge is how to map logical tables to the physical memory layout, since Tofino has a rather different memory model. In this work, we propose Selfish, a hardware-software integrated gateway system to handle growing cloud traffic with efficient on-chip memory usage. First, Selfish consists of both Tofino-based hardware gateways, XGWH, and x86-based software gateways, XGW x86, for table sharing. Second, Selfish conducts horizontal table splitting among hardware gateway cluster in a region to further reduce the number of table entries stored in each hardware gateway. Third, Selfish conducts table compression on each hardware gateway in order to greedily fit more table entries into the single node. We elaborate on these designs in the following slides. The cloud traffic also follows 80-20 rule. Based on this observation, we formulate principles of hardware and software cooperation. First, XGWH stores few key tables for basic cloud services, frequently hit by the majority of traffic. Second, XGW x86 maintains volatile tables or very large stateful tables that cannot be fit in XGWH. Third, unstable new services with less traffic are carried by XGW x86, while major service with heavy and stable traffic are turned over to XGWH. As an example, the SNAT table stores per-flow states of hundreds of millions of entries is kept in software. After table sharing, we sharply reduce hardware cost from hundreds of software gateways to 10 hardware gateways for major traffic processing and 4 software gateways for fallback traffic processing. In the region, we split table entries horizontally based on VNI into different gateway clusters. For horizontal splitting, each cluster maintains all the tables, but a portion of entries from each table, compared with vertical splitting that splits different tables of all entries into different clusters. Horizontal splitting has many benefits. First, adding a new tenant into the cloud will only cause gateway updates within one cluster. Second, the failure of one cluster will not influence others in the same region. To achieve load balancing, we can also use flow-based hashing. However, load balancing by hashing is blind. By contrast, horizontal splitting can precisely manage its traffic load on a particular cluster simply by adding or deleting the corresponding entries. On a single gateway, we further conduct pipeline-aware memory optimizations, including pipeline folding and table splitting between pipelines. XGWH can originally reach 6.4 Tbps forwarding throughput if the 4 pipelines contain the same forwarding tables and work in parallel. The throughput can further be increased by adding more gateways in a cluster. That is, for XGWH, throughput is sufficient and can be easily extended while memories are in real shortage. Accordingly, we propose pipeline folding as a trade-off to sacrifice the throughput by reducing the working pipelines by half for doubled memory capacity in each folded pipeline. After pipeline folding, egress pipe 1 and egress pipe 3 and the pipes behind them contain the same table entries. To reduce the table redundancy, we can use hashing to further divide the traffic into different pipelines so that different pipelines can store different tables. In this way, less table redundancy produces more available memory to store more table entries. Separate IPv4 and IPv6 tables lead to separate table update and expansion. However, since traffic ratio of IPv4 and IPv6 is changing constantly, separate tables may cause memory waste due to the inefficient memory usage. Our strategy is to pool IPv4 and IPv6 memory resources, ensuring that ratio of IPv4 and IPv6 can be adjusted arbitrarily. When programmable ASIC chips are taped out, the SRAM and TCAM ratio is fixed and TCAM is much less than SRAM, but the table lookup requirements of Alpm or exact match change over time. We leveraged a Alpm scheme proposed by Henry Wang to flexibly adjust the length of prefix stored in TCAM and SRAM as a trade-off between lookup efficiency and TCAM consumption. Let's see XGWH's memory usage after optimizations. For the two major tables, after pipeline folding, the memory usage is reduced by half. After table splitting between pipelines, the memory usage is further reduced by half. In IPv4 and IPv6 table pooling, we extend the IPv4 key and therefore the TCAM usage grows. Meanwhile, we also compress the IPv6 key. The result is decreased SRAM usage. Finally, after conducting Alpm to reduce TCAM usage, the TCAM occupancy is greatly reduced to 11%, while the SRAM occupancy is doubled to 36%. The overall memory consumption of all tables is 69% of SRAM and 32% of TCAM. Let's see selfish performance in the real deployment. For a single node, the hardware gateway lowers latency by 95%, improves throughput by more than 20 times in BPS and 71 times in PPS compared with the software gateway. During a large online shopping festival, Selfish's packet drop rate is reduced tremendously even in the peak hours, thanks to the very large safety margin provided by Tofino's high-capacity pipelines. We summarize our work as follows. In this work, we investigate the CPU overload problem in cloud gateways. We address the problem by accelerating the cloud gateways with programmable ASICs with a much larger safety margin. To resolve the memory shortage issue, we propose techniques such as hardware-software co-design, horizontal table splitting among gateway clusters, and single-node table compression. Selfish is first P4-based cloud gateway in the industry. Thank you for your time.
So we will move on to our next video. And once we get the chair back on, we will circle back to questions because he will be the one gathering the questions from Slack. So please stand by. We'll move on to the next video and we'll do questions at the end. Thank you, everybody.
Down first. It would be like
Hello everyone, I'm Inda Zhang. Today it's my pleasure to present our paper, Cocoa Sketch, High-Performance Sketch-Based Measurement of Arbitrary Partial Key Query. First, discuss the background. Network measurement is important to many network applications, where each application often needs a measurement defined over one key. Here, we define the key as a combination of fields extracted from the packet header. For example, traffic engineering needs the measurement of source IP and destination IP pair, and flow scheduling may need the flow size defined over 5 tuple. In addition to the above applications that only need the measurement of one specific key, many applications need the measurement over multiple keys. Let's use DDoS detection as an example. For DDoS detection, it is often hard to predict which keys are relevant to future attacks. Therefore, we have to track the flow size of multiple keys and find the abnormal data from them. Like DDoS detection, there are also some other applications that may need the measurement results of multiple keys, like route management and rate limiting. For these applications that need measurement over multiple keys, we need to ideally support the arbitrary partial key query. Specifically, before measurement, operators only need to predefine a broad range of keys, which we call the full key, that incorporates all keys that may be queried in the future. After measurement, we can query the flow size of any key that is a part of the full key, which we call the partial key. The arbitrary partial key query enables a more flexible way of querying flow size, where we can query the flow size of multiple partial keys without predefining each key to measure. However, we know that prior works on network measurement often focus on single key sketches. These sketches have to configure the sketch based on the specific key provided by the operator, and they can only provide the flow size defined over that key. Prior works have shown that such sketches can achieve good accuracy, throughput, and memory usage when measuring one specific key. So, what about reusing prior single key sketches to support measurement over multiple keys? The first way to reuse single key sketches is to specify all keys that may be needed before measurement, and configure one single key sketch for one key. Prior sketches often support measurement over multiple keys in that way. However, we should know that such a solution needs too many resources. We cannot support too many single key sketches, especially in hardware platforms where the resource is often limited. This table shows that the computing resource to support one single key sketch is around 20% of the total resources. Because such a resource grows linearly as the number of sketches increasing, we can support at the most 4 single key sketches simultaneously. The second way to reuse single key sketches is to build one single key sketch for estimating flow sizes of the full key, and recover the flow size of partial keys from full key. Note that the size of a partial key flow can be represented by the full key flows. For example, if the prefix of source IP is a partial key and the source IP is a full key, we can recover the flow size of a partial key flow by summing up 256 specific full key flows. However, single key sketches cannot provide the accuracy guarantee for the result of partial keys after recovery. These figures show that the error of recovering from full key flows is much higher than that of building one single key sketch for the partial key. In summary, reusing single key sketches cannot achieve good performance. Our target is to find an algorithm that can support arbitrary partial key queries, achieving fidelity, efficiency, and compatibility. However, building one single key sketch for one key cannot achieve efficiency and compatibility because it needs too many resources to support multiple sketches, and too many resources prevent it from implemented in hardware platforms. Furthermore, building one full key sketch cannot achieve fidelity because it cannot provide accuracy guarantees for partial keys. So, is there any better solutions to achieve all these requirements? To support arbitrary partial key queries, we first cast it to the subset sum estimation problem. As shown before, the size of a partial key flow can be represented by the sum of a subset of full key flows. Therefore, the query of partial keys can be regarded as a kind of query of subset sum. Based on the theory of subset sum estimation, to achieve accuracy guarantees for all partial keys, the algorithm should minimize the variance sum of all full key flows. Unbiased base saving is a state-of-the-art of the subset sum estimation which supports incremental updating. To minimize the variance sum, for each arriving packet, it will insert the packet into the bucket with minimum collisions with other full key flows. We will use examples to illustrate its insertion. For each incoming packet, it will first check whether the full key is recorded. If it is recorded, it will be inserted into the corresponding bucket. That is, the size of the bucket will be incremented. If the full key is not recorded, it will be inserted into the bucket with minimum size. That is, the size of the bucket will be incremented, and the full key will be replaced probabilistically. Since arbitrary partial key query is a kind of subset sum estimation, can we directly apply unbiased base saving to address this problem? Unfortunately, no, because unbiased space saving has two main limitations when it is applied in network measurement. Therefore, we designed the Cocoa sketch which can address the limitations of unbiased space saving while keeping fidelity. The first limitation of unbiased space saving is that it needs too many memory accesses. As shown before, unbiased space saving needs to check all the buckets to find the bucket with minimum collisions and update it. However, there are often thousands of buckets. Scanning all of them takes too much time and prevents the algorithm from catching up with the throughput of network traffic. To address this limitation, we propose stochastic variance minimization. Unlike unbiased space saving, which needs to check all buckets, we only check D hash index buckets and update one of them whose collision is the minimum. The key question is how to set D to achieve a good trade-off between accuracy and throughput. Note that unbiased space saving is equivalent to the sketch that D is equal to the total number of buckets. It achieves small error but low throughput. If D is set to 1, the throughput is high but the error is relatively larger. With increasing D, the accuracy is improved while the throughput decreases. We show that in network traffics which are often heavily skewed, setting D to 2 or 3 is enough to achieve high accuracy with little accuracy drop. But why such a small D can still achieve high accuracy? Before showing the intuition, we first show how unbiased space saving performs in heavily skewed flow distribution. Remind that unbiased space saving will only update the bucket with minimum collisions. Therefore, for those large flows, their bucket will mostly be updated by the same flow, and their collisions from other flows is small. For most small flows which are often not recorded, they will always be inserted into the bucket with minimum size like a load balance process. In the long run, the distribution of size will be shown as in this figure. If we set D to 2, we will only update the bucket with minimum collisions among two mapped buckets. In that case, other flows will still avoid collisions with large flows, so the large flows can still enjoy the low collision rates. For most small flows, they can only try to balance the collisions in two excesses. Although the effect of such load balance is not as good as that of unbiased space saving, based on the power of two choices, which is widely used in prior works of load balance and caching, we can also balance the collisions well in only two excesses, and the gap between it and the optimal effect is relatively small. In the long run, we can find that the distribution of D is 2 can approach that of the unbiased space saving. The second limitation of unbiased space saving is that its circular dependencies make it cannot achieve good performance in hardware platforms. Circular dependency is that the updates of variables depends on each other. In unbiased space saving, we need to find the bucket with minimum size and update it. Therefore, for each bucket, whether it needs to update depends on whether its size is smaller than others, which forms a circular dependency. Such circular dependency prevents the algorithm from pipelining. For some hardware platforms like FPGA, circular dependencies will lead to low clock frequency. Some hardware platforms like Typho switch cannot support circular dependencies. To address this limitation, we further propose circular dependency removal. Note that for stochastic variance minimization, there are also circular dependencies among D hash index buckets. After removing circular dependency, we run D independent stochastic variance minimization, each with one bucket. To control the error, we report the median result of these D buckets. In summary, we first propose stochastic variance minimization to reduce the memory accesses. Our basic Cocoa sketch, which uses this technique, can achieve both high accuracy and high throughput in software platforms. To further exploit the parallelism of hardware platforms, we propose circular dependency removal. Our hardware-friendly Cocoa sketch, which uses both techniques, can also achieve good performance in hardware platforms. In our paper, we also prove that our Cocoa sketch achieves fidelity. That is, the error bounds of all partial keys are the same. Then, we show the evaluation result to compare Cocoa sketch with prior sketches. We conduct extensive experiments on 2 real-world traces on 3 tasks related to flow size. We implement Cocoa sketch on 4 platforms and show their performance. First, as for the accuracy, we can find that Cocoa sketch can achieve high accuracy for both single key and multiple keys, while prior single key sketches can only achieve high accuracy when measuring one key. For single-thread throughput in CPU, we can also find that the throughput of CocoaSketch is not affected by the number of keys needed, while the throughput of other algorithms decrease with the number of keys increasing. We also compare the resource usage to achieve the same accuracy in hardware platforms. In the data plane of terminal switch, we can implement at most 4 elastic sketches at the same time due to the resource constraint, while CocoaSketch only needs less than 10% resources. Finally, we conclude our work. In this paper, we discuss the problem of the arbitrary partial key query. We show that reusing single key sketches is a mismatch with the requirements of partial key query problem. To address this problem, we first cast the arbitrary partial key queries to the subset sum estimation. The challenge of CocoaSketch lies in how to practically apply the theory to the partial key query problem. We propose 2 main techniques, stochastic variance minimization and circular dependency removal to achieve fidelity, efficiency, and compatibility. The source code of CocoaSketch is available at GitHub now. That's all of my talks. Thanks for attention.
Thanks for the nice talk. First of all, I would like to give an apology on behalf of Shabas. So the network at Purdue is down and he asked me to take over. So I'm Sangeeta Abdujyoti. I'm an assistant professor at UC Irvine. I'll be handling the session until he can be back up. Thanks again for your nice talk, Inda. So we are waiting for questions on Slack. So please go ahead and post any questions you have on the Slack channel. So yeah, we have a question that's coming in. Yeah, meanwhile, can you talk more about the comparison with hardware platforms?
Sorry, comparison with what?
The hardware platforms that you compared with?
Like comparison between the FPGA and Tofino switch, or comparison with other algorithms?
Yeah, FPGA and Tofino.
Yeah. In fact, in FPGA we can support more. We can support more. In fact, in FPGA we can support the circular dependencies, but it may lead to low frequency. But in Tofino switch, we can directly not. We cannot support such circular dependencies, and there are also more constraints in Tofino switch, like they cannot support the divisions accurately, and they can only support approximate division based on the highest 4 bits, and that's
okay.
So thanks, Sangeeta, so much for taking over. I have no idea. I thought I will be in Purdue, so the network will be fast, but I should have stayed home. Otherwise, it seems like so. Thanks again. I'll take it over from here. So yeah. So again, sorry, I didn't get the chance to watch your talk, but maybe what we can do is we can come back to your talk when we have more questions there. So in the meantime, I'll move on to the next talk, and then we can take up more questions on Slack. So thanks again. I hope it was a great talk. Sorry for missing it. So moving on, we have Red Plane, which is about enabling fault-tolerant stateful in-switch applications. Our speaker is Daeho Kim. He is a 5th-year PhD student at Carnegie Mellon University. His research interests are in systems and networking, with a recent focus on building abstractions for in-network computing, primarily for enabling better elasticity and resiliency. So we'll let the video take over from here.
Hi everyone, my name is Daehyuk Kim. I'm a PhD student at CMU. In this talk, I'll be telling you about how to build fault-tolerant stateful in-switch applications with our system called Red Plane. This is a joint work with Jacob Nelson and Dan Port from Microsoft, and my advisors via Sekar and Srinivasation from CMU. To give you a context of this work, in traditional networks, switches are just a stateless packet processor that forwards packets based on simple match action rules. In contrast, in today's networks with programmable data planes, network switches become a stateful in-network compute machine that can perform some stateful actions. A key enabler for this is the recent advance of programmable switching ASICs such as Intel's Tofino chip, which can process a few billion packets per second at line rate while executing some stateful operations for each packet. By leveraging this new technology, recently there have been many works that demonstrate the feasibility of various applications running on switches, which are called in-switch applications. This includes conventional network functions such as load balancer and NAT, and more innovating use cases such as network monitoring and accelerating distributed systems. While many recent works have shown the performance benefits of in-switch applications, there is one important problem that has not been explored well, which is handling switch failures. So what happens to the applications when a switch fails? Let's take a look at an in-switch NAT as an example. Suppose that the NAT has been deployed at 2 switches in the network. Initially, this red flow is routed to the NAT 1. Now, the switch running the NAT 1 fails. Since today's networks are typically engineered to mask such a failure by providing redundant path, the upstream switch can route the flow to an alternative switch. Packets now arrives at the NAT 2, but since this NAT instance does not have the flow state, packets cannot be processed and the connection will be broken. While I use the NAT as an example here, switch failures can lead to incorrect behaviors of various stateful applications, including other stateful network functions. Indeed, recent measurement studies in production networks have shown that switch failures are common in practice. So how to make in-switch applications tolerant to switch failures? Since fault tolerance is a well-studied area in traditional server-based systems, we've looked at existing fault tolerance mechanisms to see if we can apply them to the in-switch applications. In this example, there are 2 switches and one is the backup for the other. We first try to adapt checkpoint recovery mechanism through the control plane and the external state store. When a packet arrives and updates the state, it periodically takes a snapshot and transfers it to the external state store, and populates the recorded snapshot for recovery when a switch fails. To achieve a consistent snapshot, data plane execution must be paused and packets need to be buffered during the snapshot period. However, due to the lack of such a capability and limited data to control plane bandwidth in the switch architecture, this is impractical today. We also consider a state machine replication approach using chain replication in the data plane. Packets are forwarded through a sequence of switches, each of which updates its state and forwards the packet to the next switch in the chain. However, the state updates are delivered over an unreliable channel, so these messages can be lost or reordered, violating correctness. And using one switch to replicate another switch's state makes poor use of limited switch memory. It may also require changes to the routing policy, since a packet needs to be routed to a specific switch in the chain, depending on whether the packet updates or reads the state. So this exercise shows that existing approaches designed for server-based systems cannot be directly applied to in-switch applications, and motivates us to design a new solution. Based on the takeaways from this exercise, we designed RedPlane, which provides a fault-tolerant state store abstraction for in-switch applications. Essentially, RedPlane provides the applications with a one big fault-tolerant switch abstraction by offering APIs that allow developers to easily enable RedPlane in their applications, providing a protocol that correctly replicates the application state entirely in the data plane, and leveraging an inexpensive replicated state store implemented on commodity servers. While this idea of replicating state to the external state store in the data plane sounds simple, we had to address several challenges to realize this approach. First, it is challenging to correctly replicate the state entirely in the data plane. To explain this, let me use a strawman where we adapt the strict correctness used by server-based replicated systems, which typically consists of exactly one semantics and linearizability. To achieve it for every state update, the switch needs to buffer output packets until the state is successfully replicated, and the replication messages must be delivered in order and reliably. However, in today's switch data plane, it is very expensive or infeasible to implement such functionality. So our question is, what is the right definition of the correctness for in-switch applications? And is it possible to realize the correct replication without high switch resource overhead in the data plane? Even if we could correctly replicate the state for an app running on a single switch, there's another challenge when multiple switches are involved. When a switch fails or is being recovered, existing routing policy can route packets to an arbitrary switch, which may be unpredictable. In this example, the upstream switch initially routes the read flow to the switch 1. And when the switch 1 fails, it starts routing packets to another switch, which is switch 2 in this case. But we don't know if the flow will be rerouted through switch 2 or 3 in advance. In such a case, what we need to ensure is that the packet must be able to access the correct state irrespective of the location of the current switch. And the last challenge is to deal with high traffic rate of the switch. Since the switch data plane can operate at up to a few billion packets per second, if every packet needs to access the state store, it can not only degrade the application's performance, but also exceeds the state store's processing capacity, which is typically much lower than the switch's capacity. To address these challenges, we developed RedPlane that provides a fault-tolerant state store abstraction to in-switch applications with 4 key ideas. Based on our understanding of various types of applications, we first defined linearizability-based practical correctness for in-switch applications, and provide bounded inconsistency mode for write-centric applications for better performance. And our sequencing and lightweight retransmission mechanisms realize our correctness model in the switch data plane. Lastly, our lease-based state management guarantees correctness even when multiple switches are involved during failover or recovery. And it also allows local reads for better performance. To use RedPlane, developers implement their apps with RedPlane API in P4. Then they compile it with a vendor-specific P4 compiler and load it to the ASIC. At runtime, while the app running on the ASIC processes packets as usual, RedPlane allows it to replicate the latest state to the external state store. We implemented RedPlane API and the runtime component as modules in P4. And using the API, we implemented in-switch applications, including canonical network functions. We also implemented replicated state store running on servers in C++. We evaluated RedPlane using a testbed consisting of 2 Tofino-based programmable switches, 4 regular switches, and 10 servers. Now, let me show you a few performance results of RedPlane. So, how does RedPlane affect application latency? To understand the performance implication of RedPlane under failure-free operation, we measure per packet processing latency of NAT that is implemented either on switches or on servers and with and without fault-tolerant support. Here, this graph shows the CDF of the latency for 3 different approaches, and the x-axis is log-scaled. Compared to the in-switch NAT without fault tolerance, RedPlane-enabled NAT shows the same median latency with a slightly longer tail due to the state initialization overhead. Compared to the server-based implementation, there's obvious benefit of more than 6 times shorter median latency and 4 times shorter 99th percentile tail latency. Then how fast the end-to-end connectivity can be recovered with RedPlane. Again, we use NAT as an example, and I perf to generate end-to-end TCP workload. Without failure, the end-to-end throughput is around 80 gigabit per second. When a switch 1 fails without RedPlane, packets are rerouted to another switch but dropped since there is no state for the flow breaking the TCP connections. In contrast, RedPlane-enabled NAT successfully maintained high throughput when the switch fails and recovers after short disruption, which is less than a second. This recovery time is affected by both an upstream switch's failure detection and rerouting time, and red plane's lease period, which is configured to 1 second in this experiment. In our paper, we also have other evaluation results, including the bandwidth overhead and switch resource overhead of the red plane protocol. We also show the correctness of our protocol using model checking. So please refer to our paper for more details. To conclude the talk, switch failures can affect the correctness of stateful in-switch applications. To solve this problem, today I introduced red plane that provides a fault-tolerant state store abstraction with 4 key ideas. Our evaluation shows that it provides fault tolerance with minimal performance and resource overheads. Please check out our paper and GitHub repo for more details. With that, I'm happy to take any questions. Thank you very much.
All right, awesome. Really great talk. So I think let's move on to the Q&A. So one of the questions that I'll start with is you're introducing a new plane in this whole stack of the SDN stack. We have control plane, data plane. So there's a new plane that you're adding, and it seems like the premise is that you're adding some external servers that the switches can talk to in order to maintain state in case of failures. One question here is, why can't the control plane servers themselves or the control plane itself can maintain that state and switches can interact with them? Because these servers are all these planes are already fault tolerant. So do you have any insights on that?
Yeah, that's a great question. So I guess your question is about why can we use this control plane, the external controller, SDN controller for making this state tolerant to switch failure. I think that's a valid point. And actually, we have some comparison with that approach in the paper, as well as in the presentation. I mentioned this control plane based approach as a kind of one of the strawman solution. And one of the, we can definitely use that for certain types of applications, such as read-centric application, where the state is not that frequently updated. But for some switch applications where the state is very frequently updated, such as some packet counter or other the applications, I think this control plane based approach wouldn't be able to keep up with that update rate, and probably you can meet some state update, and then that can affect the correctness of the entire protocol. So that's the kind of,
Okay, so we have some questions on Slack. So one question is from Aditya. So I think his main question is about what is the difference between red plane's approach and the work that has been done already in direct state management in network functions. So I'll just add to what he has said further is, so we know that we need the switch data plane performance. There is a need there and the corresponding challenges. But what is the fundamental thing here in terms of maybe correctness guarantees or some algorithm that you're implementing that differentiates it from, say, the NFV existing solutions we have?
Yeah, I think that's a valid question. It's a good question. So I think, as you said, one of the key difference between this existing server-based NF for tolerance work, and this is the speed of this state update. For example, in the switch, we can, this state can be updated in theory, can be updated at a very high rate, like few hundreds of gigabit per second. And in most of the server-based for tolerance work, what we did is, maybe there are multiple approaches, but in general, what we did is to just buffer a packet until we replicate the state, or we can fetch the state from the old data plane or some centralized controller or the state store. But we cannot directly apply such an approach because of these characteristics of switch data planes, like high speed and lack of this functionality and capability. So that's why we propose this data plane based approach and leverage this inexpensive external state store, server-based state store and their memory. So yeah, and then because of that design, our design choice, we introduced some new protocol, and that requires some a new correctness model for in-switch applications.
Yeah.
Okay. So there is another question from Kyle about like the data plane resource itself. Like, is your solution like, does the resources that you use on the data plane, do they scale with the size/count of the registers and blocks or the tables that you utilize? Like, is there, how well does it scale, and do you have any like sort of thoughts on that? Yeah.
Right. So yeah, so in our experiment, our workload, our assumption in terms of workload is there are like 100K concurrent flows, and there are some state maintained by red plane, which scales up by this number of concurrent flows. So for example, we need to maintain some per flow information, such as lease expiration time and the sequence number, current sequence number, and last acknowledgement number, and so on. So those state size grows as we increase the number of concurrent flows. And even with this 100K concurrent flows, it consumes at most less than 13% of the entire switch resource. So I think that's a reasonable kind of trade-off and cost.
Okay. And to sort of continue on that thought, like, so one question is like, you talked about this like read-centric and write-centric applications, but it seems like the state that you're consuming or the amount of interaction that you may have with the external store depends highly on the characteristics of these workloads.
Right.
So are you optimizing on that, or just relying on the workloads? Like, okay, the workloads, if some workload is exhibiting some sort of freaky way of like updating the weights, then it's up to them and we don't do anything there. Like, what are your thoughts?
Yeah. So currently we don't touch anything on the application. So we just take the application as is. So that's why, so if you look at our evaluation, you can see some write-centric applications. For example, like some worst case scenario where like every packet updates the packet counter. And if we need to synchronously replicate the state, then I think that introduce like a very high overhead due to this replication protocol. So yeah, so because like we don't modify the application logic, and that's why this write-centric application is a kind of currently in the current design is a kind of worst case scenario or worst case workload in our protocol. But as you said, if we can modify or optimize the application logic a little bit to support this fault tolerance, I think that's a very interesting direction we can think of. Yeah.
All right, awesome. No, again, great talk and great work. Thank you so much for giving the talk. So let's move on to our last talk in this session, and also the last talk of our today's first day of the conference. So it's about revisiting the Open vSwitch data plane 10 years later. So basically, it's the talk about the Open vSwitch like software switch that we have seen that has been rapidly used and is still being used throughout the community, both in industry and academia. So I believe the authors of that switch are now going to tell us what has happened since the last 10 years and where we are heading in that area. So our speaker is William Tu. He's a staff engineer at VMware, working on software-defined networks and Open vSwitch. He received his PhD from Stony Brook University, and he has been working on network and systems research, primarily focusing on data plane optimizations, I believe. So with that, we'll let the video take over.
Okay, thanks for coming to this session. I'm going to talk about our paper, Revisiting the Open vSwitch Data Plane 10 years later. I'm William Tu. This is a joint work with Yihan Wei, Johnny and Tichi, Ben Faf from VMware and Queen Mary University of London. So what is Open vSwitch? Or OVS. So OVS is an open source software switch that runs on multiple platforms. And today, there are many commercial products using it. For example, DigitalOcean, OpenStack, VMware NSX, and also popular for the container network cases. For example, Red Hat OpenShift, VMware and Tria projects. And also there are so many research projects using OVS for SDN network. So Usually, when people are doing software-defined network, they have a SDN controller. The SDN controller has all the high-level network policies. For example, how a VM can connect to the another VM, or how the containers can talk to each other, what kind of flows or what kind of traffic should be forwarded or should be dropped due to based on the design of a SDN controller. So OVS is a component that enforces the policy through the OpenFlow protocol. The design of Open vSwitch has two components. One from the OVS vSwitch-D, the slow path. The other, we call it a fast path, or the OVS data path, which usually reside at the operating system kernel. So when the first packet comes into the OVS, usually it will miss the OVS fast path or the OVS data path. It goes to the slow path to the OVS vSwitch-D. It look at the open flow tables. It insert a cache entry into the data path, and the subsequent subsequent packet will go through the fast path, the data path. The design was mentioned in the NSDI 2015 paper, the design and implementation of Open vSwitch. So we call this classic OVS design. It's a split user and kernel model. Over the past years, this model give us some issues. For example, performance. At that time, when OVS started about more than 10 years ago, the most performant way to do packet I/O is at the operating system kernel. So you roll the kernel module, you can get the packet from the device driver. Of course, these years we saw DPDK, we saw NetMap showing very good high performance packet I/O by doing kernel bypassing. Also, when developers want to add a new feature to OVS, for example, over time we add different tunnel protocol, we do bug fixing, we do several different new features. The split model requires the developer to get the permission first from the Linux kernel community to push the code into the kernel module. And after we get the permission, we developer work with the OVS community to get the code into the user space component. So because of this split user and kernel module, the developers takes more time to add new features to OVS. When it comes to the bug fix or when we want to upgrade a new system, the split model also gives us some headaches. For example, a fix need to happen on both places, and sometimes customers run older version of kernel with newer version of the OVS vSwitch-D, or the other way. So this split model, which has two software components, give us a lot of maintenance, operability overhead. A couple of years back, we start to look at another solution called eBPF data path. So eBPF is a new Linux kernel technology that allows you to push the eBPF code into the Linux kernel, and it provides a verifier that guarantees your code is safe running in the kernel. So the idea is that we ship OVS and we write the OVS data path in an eBPF implementation. And at runtime, we push this eBPF data path into the kernel so that packet will hit this eBPF data path and do the processing in the kernel space. However, our implementation, this was a couple of years back, we found that there's about 10 to 20% performance overhead due to our performance, due to our implementation. And also for the maintainability part, because right now it's a single entity, single OVS vSwitch and OVS eBPF data path. So developers actually benefit from this design. They need to write new features in eBPF data path and OVS vSwitch-D. Also, from the operation point of view, when we want to upgrade or bug fixes, it's no longer two separate components. So it's OVS vSwitch-D and the eBPF data path. And most of the existing networking tools like TCP/DOM, IIF config remains working. There's another solution or popular OVS version called OVS DPDK. So the idea of OVS DPDK is that it uses a DPDK kernel bypass library. So on the right-hand side, you can see, for example, a device E0 will be unbind from the Linux kernel and bind it to the DPDK library. And the driver will be running in the user space, and the networking tools need to be use the link. We have to switch to use the DPDK's networking tools built on top of DPDK. And OVS DPDK or OVS data path is built upon this DPDK library. OVS DPDK right now shows very, very good performance, usually close to the line rate. It's an ideal setup for high performance network appliances. For the maintenance point of view, it's also pretty good because developer only need to work on just OVS community, not two different community, or get permission from the Linux kernel. From the operation point of view, however, deploying DPDK solution usually require managing two separate network configurations. For example, you need basic SSH or management traffic going to the Linux kernel. So usually people will have another device called ETH1, for example, and attached to the Linux kernel, and another separate device called ETH0 that bind to the OVS DPDK. So managing these two different network configuration has incurred more works, and this is because DPDK, the existing networking tools like IP-Link, TCP-DOM doesn't work with DPDK device. So because of these pros and cons, we come up with this solution called user space data path with AFXDP. So in this design, we still have OVS data path in user space. However, for the device driver, we are unlike DPDK, which runs device driver in user space. The device driver is still inside the Linux kernel. Today, Linux kernel provides this new socket type called AFXDP. So the best thing about AFXDP is that it allows you to run a very small XDP program in the device driver. So it's very fast. You can get very early access to the packet content. So if you want to do something like kernel DPDK, like kernel bypassing, so you can program this XDP program and say, for this packet, you want to do kernel bypass, send it to an AFXDP socket, let the packet be received by the OVS data path. Or for the rest of the traffic, for example, management traffic, SSH traffic, you can say in that XDP program, for this packet, go through the regular Linux kernel stack. And all the existing networking tools, for example, IP-Link, TCP-DOM still works because the device driver is still maintained by Linux kernel. So as for performance, when we are doing kernel bypass using AFXDP, it's very similar to the DPDK's performance. Of course, DPDK today is still faster than AFXDP, but there are way more optimization coming from the kernel community to improve its performance. From the maintenance point of view and the operation point of view, because it's all single component, so developer can only need to work with the OVS community to fix the bug, to add new features. So we did two performance evaluation. So first one is for virtual machine. So for the DPDK and AFXDP, because today the driver, the NIC card supports zero copy. So the packet can directly copy from the NIC to the user space data path. And when we connect it to VM, we use the vhost user. So it's zero copy between them. On the other hand, the kernel is showing more overhead, is slower because there are packet copying happen between kernel and user space due to using tab device to connect it to VM. From the containers point of view, DPDK, we found that it has pretty high overhead because the packet need to traverse to the user space data path, back to the VE's device used by the container, and back to the container network stack. However, in the case of kernel and AFXDP, because AFXDP allow us to install this this XDP program in the kernel. So using XDP or AFXDP allow us to directly direct the packet from the device driver to the VE's device to the container, showing pretty good performance. So in summary, we found that AFXDP is not always the fastest solution, but more optimization are coming up. And we also, obviously, they also support Windows. So today, AFXDP is not yet support for Windows. On the other hand, with AFXDP, we found that it's easier to patch, to develop, and to troubleshoot. And in terms of packaging and validation using popular CI/CD platform, for example, Travis and GitHub, because it's no longer a split model, it's single entity, all the softwares are there, so it's easier to packaging and validate. And with all the components in one place and user space database, we found that it's easier to do cross-platform porting because we basically have many minimum operating system specific, like kernel module for different like Windows operating system, Linux operating system, for example. With that, thank you for listening to our talk. Please try it out. Thank you.
All right, cool. Great talk. So William, hi. Is Ben joining? I think he said like he will be in the Q&A. But okay, let's start. So I think so. My first question again will be, so the paper is about the last 10 years in the Open vSwitch data plane. Can you tell us something quickly about the next 10 years in the Open vSwitch data path? Like what's happening there?
Sure. So probably not next 10 years, but like our future work for the OVS. So for example, in this paper, we talk about the decision we have made so far based on all the history of like how do we contribute to the open source community, what's the performance, and what's the interaction between different like operating systems. So for the next future work, we are working on deploying this solution to different scenarios for our customer. For example, today you can deploy a SDN solution in many cases. For example, you can deploy it in a cloud, for like Google Cloud, Amazon Cloud. In that case, probably the network performance isn't that the first priority, but they want something easier to deploy and they want something to be safe. They want to make sure your software is safe there. So DPDK might not be a solution, and then this in our case is probably good. And there are another track of work doing hardware offload. For example, Mellanox support a lot of OVS flow into their hardware ASIC and providing very high rate, high performance there. So if deployment has that solution, we also want to, this is a case we want to improve the performance. And also the SmartNIC case where you can run OVS control plane in the SmartNIC ARM core. And if the SmartNIC supports the hardware offload, of course, we want to leverage that hardware capability. So in the paper, we mentioned a couple of like performance overhead due to the processing or whatever not supporting the kernel. And one of our future work is, of course, to bring more and more the future work from optimization from the Linux kernel to the OVS. Yeah.
Okay, awesome. I think so. So we are close on time. So I'll just ask, like, connect one thing here, which I found very interesting is, so we haven't like told that, okay, user space stack, we should go there, it's faster, more adaptable, but it seemed like you touch upon a very interesting thing, which is like containers and virtual switching. So it seemed like the container is still talking to the kernel before talking to the user space switch. So maybe there is some sort of like a mismatch there. So maybe that is one of the direction that people should look into, like what should the future like network stack for containers look like? Like that's the thing that like I clicked upon here. So again, I know Ben is here, but Ben, we are like exactly on time, so we have to move on. So hi everyone. Oh, there's one more question, but I think I'll let you answer that on Slack. So thank you very much, everyone. This was the last talk of today's session. So now we have a sponsor mixer from Google and Facebook. So there, I think you should take that opportunity because Google is saying, ask me anything. So I would suggest go and ask them anything. And then similarly, Facebook, I think like the workshop that they are having is a good one for like both first year PhDs and the last year PhDs to learn what they're doing and what is like what is happening in this like new area of data center networking and so forth. So with that, thanks again, everyone. I'll see you in the sponsor mixer. See ya.